So, hello everyone. Welcome to the extra session 2. So, today we are going to talk about BHK uniformization and characterization of Gromov hyperbolic spaces. Uh, Let us recall. So, in the previous lecture,
Hello.
hello.
I had one question.
Haha, yes, please.
Uh, Before the about the question I had asked last time.
Uh-huh.
If I maybe ask this may not be related to the upcoming thing, so I may ask it in the last of the that will be, I think, better. Okay.
Okay, okay. Okay, yeah. So the general theme was to replicate this thing. So the main theorem is there is a one-to-one correspondence between the quasi-isometric class of proper geodesic Gromov hyperbolic spaces and quasi-similarity class. So quasi-symmetric class are like mappings which are quasi-symmetric plus some other extra conditions. I will not go into that one. It is just see what's going on in the uniformization of Gromov hyperbolic spaces. Uh, we discussed this uniformization procedure and we came up to this uniformization theorem which says that every proper geodesic Gromov hyperbolic space can be conformally deformed into a bounded uniform space. Okay, this is the definition of uniform space. So let X comma D be a rectifiably connected, locally compact and non-complete metric space so that the boundary is metric boundary is non-empty. Uh, if there exists a constant c greater than equals to 1 such that every x comma y in x can be joined by a rectifiable curve gamma such that minimum of length of the curve this part x to z and then z to y, this should be less than equals to c into the boundary distance distance to the boundary of z. This is known as the cone arc condition. We'll see this later. And the second thing is the quasi convexity condition. Okay, so uh, basically the proof of the uniformization theorem depends upon a result which we call the Gehring-Hayman theorem for Gromov hyperbolic spaces. Okay, let me just quickly mention this thing. Uh, so it is let x be a geodesic delta hyperbolic space and let rho such that x to 0 comma infinity be a continuous function such that so this rho satisfies again that Harnack type inequality is this thing equals to c into exponential of d of x comma y and equals to 1 by c of 0 minus epsilon d of x. So this is basically exponential of minus epsilon to d of x comma y. C. Okay, so if so we have a geodesic delta hyperbolic space and rho be a continuous function which satisfies this one for all x comma y belonging to x and for some fixed c greater than equals to 1 and epsilon greater than 0, uh, there exists epsilon naught which depends only on delta and this constant c, and M, this only depends upon C. One, such that if epsilon is less than equals to epsilon naught in, let us say this is equation A. So in equation A, then what we have is uh, then L d rho of any geodesic joining x and y is less than equals to m L d rho of any other curves joining x and y. So this is basically geodesic joining x and y, and this curve any any other curve gamma joining x and. So this is what we call as the Gehring-Hayman theorem for Gromov-hyperbolic spaces. Uh, we'll see this Gehring-Hayman theorem in the context of characterization again. But here, to prove the uniformization theorem, we use this theorem. Like, if you see the restriction, so in the uniformization theorem, if you see the restriction on this one, this comes from the Gehring-Hayman theorem only. This restriction. Basically, to prove the quasi-convexity condition for the uniform space, we are going to use the Gehring-Hayman theorem. I mean, with that one, for epsilon less than equals to epsilon naught, this conformally deformed space satisfies the first condition of the quasi-convexity condition of the uniform space. Moreover, the second condition of the uniform spaces holds for every epsilon in the deformed space. Okay, fine. So, yeah, let us introduce some two associations. So, if we see what's going on is that we have x and we are deforming into x epsilon. So we are saying this association. We will denote this association as D, which stands for damping. So x goes to x epsilon. We will denote it by D for epsilon less than equals to epsilon naught. So okay, fine. And Q we will denote by we will mean by quasi hyperbolization for each bounded uniform space omega by considering the quasi hyperbolic matrix. So if we have a uniform space omega, uh, the association Q means we are taking the quasi hyperbolic metric on this space omega. And it was like it is a result by Bonk-Heinonen-Koskela, which says that the uniform domain, uniform space is always Gromov hyperbolic. Okay, so after the quasi hyperbolization, this uniform space is now a proper geodesic Gromov hyperbolic space. Fine. So I hope this is clear. This association. What theorem A says that the composition Q, composition D basically takes a given delta hyperbolic space back to its quasi-isometric class, and decomposition Q preserves the quasi-similarity type of a given bounded A uniform space. Okay, so to achieve this, uh, we need to establish three things. I will just mention what is going on. Like, I mean, what is the what like what exactly we need to establish for that theorem A. So the first thing is if F is a quasi-isometry between two proper geodesic roughly star-like Gromov-hyperbolic space, and I haven't mentioned what do we mean by roughly star-like, but anyway, just assume that it is one property of Gromov-hyperbolic space which satisfies in most of the condition, not always, but most of the condition. Uh, so if we have a quasi-isometry between x and x, let us say x dash, uh, and x is delta hyperbolic and x dash is delta dash hyperbolic. This is the conformal deformation of x. Let us say x epsilon, and The conformal deformation of x dash is, let us say, x dash epsilon dash. Okay, so the result says that f basically induces a quasi similarity between x epsilon and x epsilon dash. So a quasi isometry between two Gromov hyperbolic space basically gives a quasi similarity between the deformed spaces. Okay, and the next result will say that the quasi hyperbolic. Yes.
Hello, can you please
Yes.
show me the last theorem? That is between two proper geodesic and what is roughly star-like you have written. What is that?
Sorry.
What is that written roughly? Proper geodesic roughly. Then after that star-like. No,
It
what is
means
written?
yeah. This is a notation. Like this is another property of space being roughly star-like.
What is the definition of being star-like in a matrix space?
Yeah, it is a metric. No, yeah, it is a metric sense. If you are looking at the star-like definition for a domain in like planar thing, it is, yeah, it is
Yes.
different to that one. It is not that thing.
No, in a domain T times X product is defined, but here is no product, right?
Yeah, yeah. So that's what I'm saying. It is different to that thing.
I am asking that what
I
is
have
that?
to. Okay, so I have to mention that thing. Maybe later I will mention it. I mean, that's kind of. Let
Okay,
me
and
just.
whose theorem is this?
You can find it in BHK paper. I have written here. In this one only.
If you write the references of that theorem, then it will be good enough.
Okay, yeah. So it
Oh,
is
yeah,
like
yeah.
in
Thank you.
this. Yeah, yeah. I've written like BHK So all the things is BHK uniformization is from this paper only.
Okay, okay. Thank you. Thank you.
Yeah.
Thank you. Now it's fine. Now. Yeah.
Okay. So where we were. Okay, yeah. So once we have the quasi similarity, we have the quasi isometry between two spaces, roughly star, Gromov-Hyperbolic roughly star-like space. We have the quasi similarity between the deformed spaces. Next result says that the basically for the uh, for a uniform space, once you quasi hyperbolize it and then take the deformation d, like damping this association d, because see, if we have a uniform space is quasi hyperbolization, this is always Gromov hyperbolic spaces, again a result by BHK. And then since this is Gromov hyperbolic, we then apply the association d, so it becomes omega epsilon. Now this identity map is basically quasi similar, and the next result is a quasi similarity between two uniform spaces is a quasi isometry in the quasi hyperbolic metric. So again, like the converse of this one, here we have the quasi isometry which induces a quasi similarity. In this one, we have a quasi similarity between two uniform spaces. Then this will give a quasi isometry once we quasi hyperbolize it. Okay, so this was the theme of BHK uniformizations, and we will see its applications later on. Okay, so like here we are going to talk about the characterization of Gromov hyperbolicity with respect to the quasi hyperbolic metric. Uh, Again, let omega comma d be a rectifiably connected, locally compact, non-complete metric space, and we define the quasi hyperbolic metric with the same length element, mod dz upon uh, delta omega z. So here delta omega z is basically distance of z to the boundary of omega. Okay, and we equip x x comma d with the inner metric again, like this one. This we have seen earlier also in earlier lectures, and we know that this is not in general. This in general the identity map need not be homeomorphism. So if it is, we call such a space as minimally nice space. Okay, so means if we have a metric space x comma d, and we associate it with the inner metric, if this is a homeomorphism, if the identity map is a homeomorphism, then we call such a space x comma d as a minimally nice space. And if omega comma d is a minimally nice space, then Uh, uh, if we cube omega with the quasi-hyperbolic metric, that is going to be complete, proper, and geodesic metric space. Okay, so for some more examples, we need some notions of domains in Rn, which works well with which are compatible with the quasi-hyperbolic geometry. So I will mention those things. Here we are going to discuss about John domains, inner uniform domains, and uniform domains. Definition will be kind of similar to, like, if you know one definition, you can just see the other definition also. So we'll see that one. Okay, so we'll just go back to the, like, we'll just skip this one and go back to the definition. So uniform domain I have already, like, mentioned earlier also. Say, like, if every pair of points can be joined by a rectifiable curve which satisfies double planar condition and the quasi-convexity condition. Okay, uh, this is a definition for John domain with center. So this is just regarding the uh, this works like in this one. We have that omega is always bounded. The same thing, like, if every point x belongs to omega can be joined to x naught by a rectifiable curve gamma, which satisfies length of gamma x to y is less than or equals to c into delta omega of y, where y belongs to gamma. So, like, we have x naught and we have any point x. This can be joined by this curve if you take any point y. So the length of this thing is less than or equals to c into the distance to the boundary, like, distance of this y to the boundary. Okay, and again, C uniform domain, inner uniform domain is the, like, the first condition will be there, double planar condition, and this condition will be replaced by the uh, inner metric, so C into delta omega lambda omega x comma y. Okay, so here we have seen that a John domain with center x naught, this is always a bounded domain. So for unbounded domains, we have this definition. It means that just remove this definition from the from the uniform domain. We have the definition of John domain. So this is a general definition for any, like, we if I if I'm saying John domain, I mean this definition. So basically they are equivalent. Once the domain is bounded, this condition and this condition, basically they are equivalent. Here's the thing. Okay, fine. Here's some. Okay, so this is just an explanation of conar. So basically, what does it mean uh, to have this one? It means that between any 2 points, we can fit a curvilinear cone inside the domain, and which looks like whose axis will be the gamma, vertex at x, and center at x naught. So the fatness will be at the center. It will be like we are having a carrots kind of thing, and here it is a, like, fatness will be at the center x naught, and this is a point x. So, like, in a domain we can we can fit a caret having the vertex at x and the fatness at x naught, means the fatness of the caret at the center x naught. So this is what we mean by a conar condition. Okay, so so here's some examples. So uniform domain is contained in inner uniform domain, and inner uniform domain is contained in Zorn domain. So every Lipschitz domain is uniform domain, and every bounded convex domain is again uh, uniform domain. Uh, we have domains, we have unbounded domains, convex domains, which is not a John domain. So this kind of domains are not John domains. And removing us, uh, this domain is again, this is John, but not uniform. Again, this can be seen easily because of the, the quasi-convexity condition fails here in this kind of domains. And a Jordan domain is uniform if and only if its boundary is a quasi-circle. So quasi-circle will be familiar to people who are working in, like, quasi-conformal geometry. Okay, and a bounded simply connected domain with piecewise smooth Jordan curve boundary is John domain if and only if there is no outward pointing cusp. So in joint domains, inward pointing cusps are allowed, but not outward cusps. Okay, so we'll move ahead. Uh, so we'll now mention a very important result which provides a complete characterization of Gromov-hyperbolic domains omega in Rn. So by Gromov-hyperbolic domain omega in Rn, it means that we take a domain in Rn and we say this is Gromov-hyperbolic domain if this omega comma k omega is a Gromov-hyperbolic space. So for this, we need to introduce two conditions, Gehring-Hayman condition and Ball separation condition. So let us just see what is Gehring-Hayman condition. So consider the Poincare disk model of the hyperbolic space and let gamma be a hyperbolic geodesic joining x and y. Then what we have is that uh, length of the curve gamma is less than or equals to pi by 2 into modulus x minus y. Okay. So this basically says that this hyperbolic geodesic is essentially the shortest curve in the Euclidean sense. Okay, like we have this constant pi by 2 and length of the curve gamma is less than or equals to x minus y. So we'll see the proof of this one. So here we have a we have our disk and we have x comma y. Geodesics will look like this: arc, like part of arc of a circle, which is perpendicular to the unit circle, and let us say the center with some center and radius r. Okay, so from this one, it is clear that the gamma, so gamma is this red curve, red part of this circle, and Euclidean length of gamma is basically r theta, means its arc length, and modulus of x minus y is nothing but uh, this is basically, this part is basically theta by 2. So we need to check this part only, and this part will be equal to this one. So we will have this whole thing. So this part will be, again, we'll use the sine theta. So sine theta by 2 is basically this part upon this part. So we have x minus y is equals to 2r sine theta by 2. Okay, and so length of gamma upon modulus of x minus y, this is basically theta upon 2r sine theta by 2. So this is now basically theta by 2 upon sine theta by 2. Okay, where theta is from 0 to pi, and this will be less than equals to pi by 2. We have the desired inequality. Okay, so so this is what we have, and what Gehring-Hayman theorem says that let let omega be a simply connected domain, and u comma v is a hyperbolic geodesic in omega, and gamma is any other curve joining points u comma v. Then there exists an absolute constant c. So by absolute means this c does not depends upon while changing the curve. Okay, this c is an absolute. This only depends upon this omega. The length of this hyperbolic geodesic is less than or equals to c into length of Euclidean length of any other curve gamma joining x and y. Okay, so it means that hyperbolic geodesics are essentially the shortest curve. Okay, so this is Gehring-Hayman theorem, proved by Gehring and Hayman, obviously. And if you see the unit disk case, this will also hold as this means that this is also less than equals to c into infimum of L Euclidean of gamma. Okay, and since in the unit disk case unit disk is convex, this thing basically achieved by a line segment. Okay, so this is c into x minus y. Okay, that is why in the unit disk case we have L Euclidean of this u comma v less than equals to c into modulus of x minus y. Okay. Fine. So for a general metric space, we will define Gehring-Hayman condition and ball separation condition. Uh, so so we say that a metric space x comma d. Let us just okay. So we'll take metric space as the minimally nice space. Okay. So we say that a minimally nice space satisfies Gehring-Hayman condition if there exists a constant czh greater than equals to 1, such that for each pair of points x comma y belongs to omega, and for each quasi-hyperbolic geodesic gamma joining x and y belongs to omega, it holds that the length of this quasi-hyperbolic geodesic is less than equals to c, this constant, into length of the any other curve gamma joining x and y. Okay, and we have this ball separation condition, which says that basically there exists a constant c. uh, we are denoting bs just to indicate that it is ball separation. cbs such that for each pair of points x comma y, uh, for each pair of points x comma y, and for each quasi hyperbolic geodesic joining this one, we have that. So we have x comma y, right? So we have, so this is our domain, and we have uh, and x and y, 2 points, and we have a quasi hyperbolic geodesic joining this one. Okay, and for each curve joining x and y, wait a minute, and take any point z belongs to this one. So now if we have curve gamma which joins this part to this part, means we have these curves, these are sigma, then the ball centered at z with this radius cbs into the distance to the boundary, this will always intersect with this curve. Okay, so it means that basically it means that uh, at least one of the either at least one of the end points of quasi hyperbolic geodesics, like means this ball, let me just write it down. So we have our space x, and let us say we have 2 points x and y. We have quasi hyperbolic geodesics joining x and y, and if we take z, and if we take curves joining these two parts, let us say, okay, means these are curves sigma, then what it's saying is that ball centered at z and the radius cbs delta omega z, so this should always intersect with sigma. Okay, it means that it means that this ball, this ball either includes includes at least one of the end points, or it separates the endpoints. That is what we mean by ball separation. Okay, so if we take this neighborhood, either it will have uh, either this ball will have one of these endpoints, or it will basically just uh, wait a minute. This would be at z, so it will be large enough to take one of the endpoints in it, or it will be just separate the endpoints. Okay, it will just hit this sigma. So this is what we mean by Ball separation. So for domains omega in Rn, BHK have proved that Gehring-Hayman condition and Ball separation conditions are necessary for omega comma k omega to be Gromov-hyperbolic. Okay, and conjecture that these two conditions are sufficient also. Later on, Balog and Buckley proved this conjecture, and thus combining these two, we have the following important result, uh, which says that domain omega in Rn is Gromov-hyperbolic with respect to the quasi-hyperbolic metric, if and only if omega comma d Euclidean satisfies both Gehring-Hayman condition and Ball separation condition. This is still an open problem, which is in the same paper Balog and Buckley asked whether Ball separation condition implies the Gehring-Hayman condition or not. Okay, I hope up to this everything would be everything is clear. If any doubt, please let me know. Okay, fine. So, and here we have some more examples of Gromov-hyperbolic spaces. So basically, every inner uniform domain is Gromov-hyperbolic with respect to the quasi-hyperbolic metric, and a joint domain is Gromov-hyperbolic if and only if it is inner uniform. Uh, this is not an immediate thing. This requires some two big results. So first one is the result that Gromov-hyperbolicity gives Gehring-Hayman, and the second one is that once you have a Gromov-hyperbolic John domain, every quasi-hyperbolic geodesic is a conar. If you go back to the definition of these domains, see, I have written that every pair of points can be joined by a rectifiable curve. uh, the natural question would be when this rectifiable curve will be like when quasi hyperbolic geodesic serves as this rectifiable curve, like when quasi hyperbolic geodesic do the job of this rectifiable curve. Okay, so if we have a Gromov hyperbolic John domain, then every quasi hyperbolic geodesic satisfies this condition. Okay, so I mean our aim is to find a rectifiable curve. Quasi hyperbolic geodesic will do the job once the domain omega is Gromov-hyperbolic. So those two facts we need to use. Those two facts we need to use to prove that a John domain is Gromov-hyperbolic if and only if it is inner uniform. And quasi-conformal image of Gromov-hyperbolic domains, since every quasi-conformal maps are quasi-isometries with respect to the quasi-hyperbolic metric. Okay, these are some kind of domains. So a Denjoy domain is called, if a domain, so a domain is called a Denjoy domain, its boundaries contained, if its boundary is always contained in the real line. So let us say if omega is our, if our omega is complex plane minus these 2 points and comma 0, uh, yes, so this will be basically omega intersection R will be basically what would be an here, and so it will be bn will be an plus 1. So like we are removing the points 1 comma 0, 2 comma 0, and this will be this 1, an will be n, isn't it? This will be the thing, I guess. Yeah. So the quasi hyperbolic metric, if you see bn minus an upon an, this is basically 1 by n, and this tends to 0. So it means that the quasi hyperbolic metric is not Gromov hyperbolic with this result. Okay, this we have seen earlier also, like as in the examples. We have seen that this domain is a John domain. This domain is a John domain, but not inner uniform because it is not Gromov hyperbolic. Okay, fine. So, and this is just an explanation of other domains. So we have a domain omega d minus a vertical red segments, and these segments are like getting shrinking to getting converging towards this point, and the shrink between these two segments going uh, shrinking sufficiently fast. Okay, so that once you have 2 points x and y, and we want to join it by a curve gamma. So for the inner uniform domains, once you take this curve tending, once you take these points tending to this point P, the curves which are joining that is again getting smaller and smaller. Okay, so ultimately this is going to be zero in this kind of domains. We don't have the the first condition of the inner uniform domains, means length of the curve is less than or equals to c into lambda omega x comma y. So we won't be able to find such curve gamma because this is going to be zero. Okay, so this is again not Gromov hyperbolic because this is a John domain but not inner uniform. Okay, uh, next part, next thing is okay, fine. Now we have the characterization of Gromov hyperbolicity with respect to the quasi-hyperbolic metric. Now it is natural to ask what would be the comparison between hyperbolic metric and Gromov hyperbolic metric, and the property which we are going to compare is Gromov hyperbolicity. So uh, it is natural to ask whether does there exist any domain which is Gromov hyperbolic with respect to the one metric, but not with respect to the other metric. Okay, we'll see answer to this one. Okay, so just a quick recall on the hyperbolic metric. So a domain is said to be hyperbolic if c minus omega contains at least 2 points and they have the holomorphic universal covering map from the unit disk, and we define the hyperbolic metric on any hyperbolic domain via the pullback by this metric h. Okay, so the result is each hyperbolic domain carries a unique maximal metric lambda omega w, such that the pullback of this metric by this universal covering is the Poincare metric on the unit disk. Okay, and we define, now we have this density, so we define the hyperbolic metric H omega on omega, like in a similar fashion. Okay, and this is going to be a complete metric space, which gives the same topology, Euclidean topology. Okay, so this is the hyperbolic metric. So here this we will call as hyperbolic density for a domain omega. Okay. Now we have a comparison principle which says that if omega 1 is a subset of omega 2, uh, then lambda omega 1 is basically less than or equals to lambda omega 2. Okay. Wait a minute. I think this should be lambda omega 2, I guess. So, E something. Okay, so let me write it down here. So this is wrong. It should be lambda omega 2 z uh, is less than or equals to lambda omega 1 z. Uh, Wait a minute. So yeah. Okay. So this comparison principle will give us that again. I have to write it here. So this comparison principle will give us that lambda omega z into the distance to the boundary of z is always less than equals to 1. And okay, so we'll first see this one, this proof of this one. So let us write it down as proposition. So this says that let omega be a hyperbolic domain then lambda omega z delta omega z is less than or equals to 1. Z belongs to omega. So the proof goes like this. So we have a domain omega, and we take any point z. What we do, we take this ball. This ball will always be contained in omega. So center at z and the radius delta omega z, and let us call this domain omega dash. Okay, so omega dash is always contained in omega, and by the comparison principle we have lambda omega z at this point z is less than or equals to lambda omega dash z. Now this is a ball, okay, centered at z and the radius delta omega z. So basically this one needs to check. This is easy to check. Just one need to get the density on the ball. There's a general formula for that one, and this that will give that lambda omega dash basically less than or equals to 1 upon delta omega z, and this implies omega z into delta omega z is less than or equals to 1 for every z belongs to omega. Okay, so okay, so let me write this as remark. So observe that once we have these kind of things, uh, this bound lambda omega z and delta omega z, let us say this is less than or equals to, so this is always less than equals to 1. So it means that this hyperbolic metric is, which is nothing but influence over gamma lambda lambda omega z mod dz, this integral is over gamma, is less than or equals to infimum over gamma mod dz upon delta omega z, and this is nothing but the quasi hyperbolic metric. So we have the one side comparison equals to k omega x comma y. Okay, if we have, if we have some quantity c such that omega z, and this is positive for all z belongs to omega, then we have one side inequality also, like k omega will be comparable to h omega. So k omega is basically, it will be infimum over the curve gamma mod dz upon delta omega z, and this will be, I think, 1 by c infimum over gamma infimum over gamma dz sorry lambda omega z mod dz, and this is basically less than equals to 1 by c into h omega of x comma y. Okay, so this h omega of x comma y is basically, so once we have this one, in addition, if we have this one, we have that c into k omega x comma y and h omega x comma y and k omega x comma y. Okay, so we have this comparable. So we say that these metrics are comparable if in addition we have this thing. Okay, basically they are bilexic. So this is the important thing to note. For simply connected domains, they are always comparable, and that comes from the Kobe 1/4 theorem. So basically, for simply connected domains, we have this inequality. So in simply connected domains, we have that hyperbolic metric and quasi-hyperbolic metrics are comparable. So observe that once if we have this thing, Gromov hyperbolicity of one metric will give the Gromov hyperbolicity of other metric. Okay, means they are simultaneously Gromov hyperbolic. So if hyperbolic and quasi-hyperbolic metric are comparable, they are simultaneously Gromov-hyperbolic. But the thing is, uh, in general, this quantity can be arbitrarily small. Just take a punctured unit disk and see that one. And let us define a quantity which is infimum of this one, a c which depends upon omega, lambda omega z into delta omega z, and take the infimum. Let us define this quantity as denote this quantity as c. So we want to check when c is greater than 0. And that is a result by Bearden and Pomerenke, which says that let omega be a hyperbolic domain in C, then C greater than equals to 0 if and only if boundary of omega is uniformly perfect. In other words, hyperbolic and quasi-hyperbolic metrics are comparable if and only if the boundary of the domain is uniformly perfect. Again, we are not going to see what is uniformly perfectness means. We are just going to compare the Gromov hyperbolicity. So it means that once we have that the boundary is uniformly perfect, they are simultaneously Gromov hyperbolic. Okay, so basically the natural question is whether there exists a domain such that one of these metric is Gromov hyperbolic and the other one is not. Okay, it is clear that if boundary of a hyperbolic domain is uniformly perfect, then they are simultaneously Gromov hyperbolic. Okay, since this anti-map is going to be bilipstic. Recently, Buckley and Heron proved a marvelous result. At the same time, this is very surprising result, which says that hyperbolic and quasi-hyperbolic metric are simultaneously Gromov hyperbolic for any hyperbolic domain. Okay, so uh, so the answer to the question would be like if we are looking for the domain which is Gromov hyperbolic with respect to the one metric, but not the other, uh, such kind of domain does not exist. Okay. So like every hyperbolic domain is simultaneously Gromov hyperbolic with respect to the simultaneously Gromov hyperbolic. And for planar hyperbolic domain, we just say that it is Gromov hyperbolic. We does not we don't mention the metric because they are simultaneously Gromov hyperbolic. And the proof of this fact that they are simultaneously Gromov hyperbolic is based upon the following very interesting result, which says that basically hyperbolic quasi-geodesics is quasi-hyperbolic quasi-geodesics, and so basically hyperbolic geodesic is quasi-hyperbolic quasi-geodesic, and quasi-hyperbolic geodesic is a hyperbolic quasi-geodesic. So let us take for a is equals to 1. So a hyperbolic 1 quasi-geodesic. Okay, so hyperbolic 1 quasi-geodesic. For this a, there will be some constant h and k, so that hyperbolic quasi-geodesic gamma h is a k quasi-geodesic, and a quasi-hyperbolic geodesic gamma k will be h hyperbolic geodesic. Sorry, h quasi-hyperbolic h quasi-geodesics in with respect to the hyperbolic metric. So this is again a very interesting result, which says that basically the quasi-geodesics are basically the same curves in the hyperbolic and quasi-hyperbolic metric. Okay, fine. I would like to mention one point here. See this, we have a domain, planar domain, and we are looking for this thing. From the Gromov-hyperbolicity perspective, they are always going to be simultaneously Gromov-hyperbolic, but we have seen that they are this uh, uh, we have seen that they are bi-Lipschitz equivalent uh, if the if the boundary is uniformly perfect. Uh, what about the other kind of equivalence when the identity map is let us say quasi-isometry? Okay, uh, other is quasi-symmetric. So there is a paper by Heron on this topic. I will mention later on. So and and still this problem is completely still like okay. So if let us say if this are quasi isometry, okay, these two identity map is, let us say the identity map is quasi isometry, then basically if one is Gromov hyperbolic, the other one has to be Gromov hyperbolic. Okay, but the thing is uh, if 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 let us say omega is Gromov hyperbolic, I'm not mentioning a metric because that is going to be simultaneously Gromov hyperbolic. If omega is Gromov hyperbolic, then there are domains, Gromov hyperbolic domains, where this identity map is not quasi isometry. Is not quasi isometry. There exists omega is Gromov hyperbolic, but this identity map is not quasi isometry. And at present, I don't know whether the complete characterization is known or not. Means for a Gromov hyperbolic domain, characterize those domains for which this identity map is quasi isometry. Even for very nice kind of domains, this fails. I mean, for uniform domains, this fails. Like there exist uniform domains where this identity map is not quasi isometry, and uniform domains are always Gromov hyperbolic. So this is kind of an, I think, still an open problem. I have to check the literature, but yeah. To characterize all such Gromov hyperbolic, let omega be Gromov hyperbolic, characterize all such domains for which this identity map is quasi isometry. Okay, fine. Uh, okay, quasi-symmetry is always characterized. It is there in that paper of Heron. I will mention the paper in the references. Okay, one more thing which I would like to talk about is that Gromov hyperbolicity and the Kobe uniformization conjecture. And this is a recent result. It's just an update, which says that result of okay, so Bonk-Heinonen-Koskela proved that Gromov hyperbolic domains in the extended complex plane, they are basically precisely the conformal image of inner uniform slit domains, and they basically conjectured that inner uniform slit domains can be replaced by uniform circle domains. Okay, and recently this conjecture has been proved affirmatively, which gives us that every Gromov hyperbolic domain satisfies Kobe uniformization conjecture. So yeah, the property of Gromov hyperbolic. So we have one kind of class of domains which satisfies Kobe uniformization conjecture. So this is kind of an improvement towards the Kobe uniformization conjecture.
What is this Koebe's uniformization conjecture?
I mean, it is conformally equivalent to the circle domains. Any domain is conformally equivalent to the circle domain.
What is conformally equivalent to the circle domain?
Like circle domain means boundary components are either a point or a complete circle.
Okay.
Yeah. So like for simply connected domains, we have a complete circle. So for simply connected domains, we simply had this disk where the boundary,
Right.
where the boundary is circle.
Right.
These kind of, for multiply connected domains, we have different kind of, like this could be one other kind of thing, something like this. So it covers all the things. Kobe uniformization conjecture says that this circle domain. So for every hyperbolic domain, there is just a circle domain such that it is biholomorphic to that.
Okay. Okay.
Yeah.
Thank you.
Okay, so I will stop here. Any doubt? Any question? Okay, if not, I think we can close this session.
I'll see the recording and might ask you some.
Okay, so you can ask me through. Yeah.
Thank you, Abhishek, for the nice lecture series.
Oh, thank you
Yeah,
so much.
thanks.
Thank
Thanks.
you. Okay.
The
Thanks
excellent,
for the appreciation.
excellent lecture.
Thanks for the appreciation.
Mm.
So, Agnew, I think we can close this session.